All right, so play posit number one was constant speed, pretty straightforward. We want to get more complicated and more interesting, so we're going to do thinking about what a position versus time graphs look like if the speed is changing. So if the speed is changing, the function is going to be curved. So it's going to be a function, but it's going to be curved. So this indicates that the velocity is continuously changing. Like every infinitesimal time stamp is different than the previous. Okay, so you can't just say what's the velocity of something. You have to either say what's the instantaneous velocity at a given point, which is the instantaneous rate of change. So you can kind of eyeball the slope of the tangent. That's the slope of that red line is the how fast the object is going at t equals 0. And then you can see that the slopes kind of level off, and then the slopes are negative. Okay, so I think you all have done I rock, right? Instantaneous rate of change. Um, that's called the instantaneous velocity. That's going to be the output of our velocity function when we talk about that in class. But so if you're talking about an instant in time, you look at your speedometer, that's the instantaneous velocity. If you're talking about a time interval, that's the average velocity. So what's cool is that to calculate the average velocity, hopefully this makes sense to y'all. The average velocity, just like we did in the first one, is going to be it's t2, x2. That's my second coordinate at point B, and you've got some kind of t1, well, 0, and 30, maybe x1 at point A. If you take the slope of the secant line that is connecting points A and B, geek out with me for a second, that magically averages the infinite number of velocities. So, oh my God, look at how productive you've been. You just average an infinite number of values. If you calculate x2 minus x1 over t2 minus t1, so you can do a little bit of work, but it's not that, it's pretty cool. That is going to average how fast you're going at t equals 0, and the slope of this line, and the slope of this line, and the slope of this line, and the slope of all of those lines. And there's an infinite number of points at which you could look at the instantaneous rate of change. And there's an infinite number of points. You're going to average that, every single one of those counted equally, and that is the same as the average velocity. Okay, but we're going to be lazy, clever, and attractive, and just do x2 minus x1 over t2 minus t1. Okay, so pretty cool. Okay, warning, the average velocity washes out all the information about how you got there. There's an infinite number of ways to get from point A to point B in the same time. So you've lost some information. All you know is the average. Okay, so just to re-emphasize that point, you've got, instead of points A and B, you've got this point, and you have different paths going from, what is this, at t equals 0, you're at 15 meters away from the origin, and then you end up 35 meters away. Yeah. So question number one is, which object has traveled the least distance? Looking at this carefully, I don't love this question, but I think it's still helpful, because they're going to have different odometers, because some of these backtracked. So I should say which object had the least displacement. And they all have the same displacement because they all ended up 20 meters ahead. So some of them did it more efficiently than others. This person backtracked and then went faster. This person did nothing and then, like, oh my God, I'm running late, and ran fast. This person sped up and then backtracked and then went forward and then backtracked. Okay, but they all got to the same spot in the same time. So the ones that were doing nothing for part of the time had to make up for it by going even faster for the last time interval. But that's what average means, that doing nothing for a long time and then going really fast is going to average out to this slow and steady path B. All right? So that's my point, is that there's more than one way to get to the same spot in the same time. And we kind of talked about that, which objects backtracked. Any object that has both a negative and a positive. So it's not just negative backtracking, right? Because if you always went negative, you didn't backtrack. You just kept going farther. So you have to have some negative slope and some positive slope. Some positive slope and some negative slope. Oh, so I didn't answer the question. So let's see. So A backtracked and D backtracked. Okay, which object took the least amount of time to get to the final position? And trick question, they all took 70 seconds. So some of them did it more efficiently, or less efficiently, but then they made up for it by going faster, right? So that's why if this person had not traveled faster, right? If person C, who did nothing, then traveled at the rate of B, wouldn't have got there in the same time. Okay, hopefully that makes sense. I scanned this in from your textbook just to emphasize what instantaneous velocity means. So okay, so this is a object that's going forward slower and slower, and then backwards faster and faster and faster. Maybe some of these points are constant speed, not clear, and then it's starting to slow down. So the speed is continuously changing, and if we want to find the speed at A, what we can do is we can take the average speed from A to B, the slope of the secant line, and then imagine moving B a little bit closer, and I'm going to take the slope over a smaller time interval, move B just a little bit closer. I'm going to take the average slope over an even tinier interval, an even tinier interval. And in the limit, because we're math geeks, in the limit that B and A are pretty much as close to each other as you can imagine, you get that green line, which is the instantaneous velocity. Okay, so that's one way that textbooks help you visualize that, and hopefully this makes sense. The closer you get to flattening, hopefully it makes sense. You're going slow in this area, right? The slope of the slope here, these values aren't changing quickly. So by including more of, we're going to see close to the vertex of the parabola, you are including in your average a lot of lower values, and that's going to lower your average velocity. So as you include fewer and fewer of those I'm not going very fast values, your average value increases. That's why A is, the green line is steeper than any of these other blue lines. Okay, so it is the slope of what's called the tangent line. So some textbooks will say the tangent line is a point that only intersects the function at one point. I don't love that definition. To me, what makes more sense, I like this graph better. If you imagine any part of the graph, none of these are very curved, but if you imagine this part of the graph as, if you zoom in and you think about those little wooden train tracks that you get, if you imagine having a whole bunch of segments of those train tracks and you connect them together, what you get is a circle. And then you know how to draw a tangent to a circle, draw the radius, and then draw something perpendicular to the radius. Okay, so when I learned calculus or physics in high school, that was what visually made the most sense to me. Take some chunk of, take the chunk that you care about, zoom in, and if you imagine in this point here is going to be a really, really big circle. Sorry, my drawing skills aren't great with my tablet. If you zoom in and imagine a circle, draw the tangent to that circle. Okay, so I think that's what they're trying to do. I'm not sure what all this, I don't want to waste your time, but that's what I'm trying to think. Like, slope of the tangent line is, tangent to that circle that you could build with that little section of function track. Okay, so again, reach out in class if that's not making complete sense. Some of you have seen more of that than others. And let me move this down some. Last slide, yay. What instantaneous velocity means. So visually, I want you to know what that means, right? That's what we're going to be doing. You're going to be looking at graphs and seeing whether the instantaneous velocity is faster or slower at different points. That's really important. Mathematically, we're not going to be taking limits. I just want you to understand conceptually what that means. The instantaneous velocity as opposed to the average velocity that had a bar over it. And they have the subscript x because this is the horizontal speed, and it might also be going vertically, and then you'd say vy. So you can ignore that x for now. 3 lines means is defined as. So the instantaneous speed is that average speed in the limit that the time interval goes to 0. That's what we were doing up here with this. We were shrinking that time interval. So in the limit that time goes to 0, we're going to define that. We're going to say, that's a useful concept. I'm going to call that velocity. All right. And then you will learn later on, or you already know, that that is the derivative of the position function, right? Because what is the derivative? It is f of b minus f of a, right? That's x2 minus x1 over b minus a. That's delta t in the limit that b minus a goes to 0. Okay, that doesn't maybe completely match the terminology you learned in math, but f of x plus h minus f of x over h, right? It's the same thing, using slightly different terms, but it's the same thing. So you don't need to write this down. We're not going to be doing limits, but I want you really comfortable with what does it mean when we say v, instantaneous velocity. That's the velocity in an instant. It is velocity. It's not speed, which means if there's a negative slope, we want to include it. Remember, negative means direction. And conceptually what that means on a graph versus average. Okay? Hopefully that all makes sense. Thank you for listening, and I'll see you in class.